Something unusual is happening in the far reaches of our solar system, beyond Neptune's orbit. A group of icy objects drifts through space in strange tilted paths that can't be fully explained by the gravitational pull of the known planets. Something hidden, something powerful is tugging at them. Many scientists now believe this mysterious force could be caused by an unseen planet, a massive, distant world called Planet 9. Since the idea of Planet 9 was introduced in 2016, it has sparked fascination and debate among astronomers. But the concept of discovering planets through their gravitational influence isn't new. In fact, that's how both Neptune and Pluto were originally found, through math before sight. Long ago, astronomers noticed that Uranus wasn't moving the way it should. It sped up and slowed down in its orbit, almost as if another unseen body was pulling on it. In the 1840s, two mathematicians, France's Urbain Le Verrier and England's John Couch Adams, separately suggested that the strange motion of Uranus could be caused by the gravity of a hidden planet. They didn't have telescopes that could see this object, but their calculations pointed to where it might be in the sky. On September 23, 1846, astronomer Johann Galle and his assistant aimed their telescope at the location Le Verrier had predicted, and they found Neptune on their first try. It was a landmark moment in science, a planet discovered not by chance, but through the power of mathematics. After Neptune's discovery, many believed the solar system was finally mapped out. But once again, oddities appeared. Neptune's own orbit had small irregularities, too slight to ignore. These tiny wobbles hinted that something else might be lurking even farther out. Now, over a century later, we find ourselves in a similar situation. The behavior of distant icy objects beyond Neptune, the Kuiper Belt objects, suggests that another large body may be influencing them from the darkness. This time, the suspect is Planet 9. Some scientists believe Planet 9 could be a rogue planet that drifted into our solar system long ago and was captured by the sun's gravity. Others think it might have formed in place from the same cloud of gas and dust that gave birth to the rest of the planets. If it exists, Planet 9 is estimated to be around 10 times the mass of Earth and orbit at a distance between 400 and 800 times farther from the sun than Earth does. Finding such a distant planet is no easy task. Even with today's most advanced telescopes and cutting-edge computer models, spotting an object so far away and likely so faint is incredibly challenging. Yet scientists have gathered the strongest evidence yet that something is out there. The peculiar movements of those distant space rocks don't add up without the presence of a large, hidden object affecting them. So what exactly have researchers discovered that brings us closer to confirming Planet 9's existence? Why is this world, if it's real, so difficult to detect when we found exoplanets orbiting stars hundreds of light years away? And how did it end up so far from the center of our own solar system? The mystery of Planet 9 continues to unfold, following a tradition of using math and observation to uncover hidden worlds. And just as Uranus led us to Neptune, these icy wanders might lead us to the next great discovery in our neighborhood solar.
After more than 8 decades of searching, the mysterious Planet X finally seemed to reveal itself. At least, that's what astronomers believed at the time. On February 18, 1930, a young astronomer named Clyde Tombaugh, working at the Lowell Observatory, noticed a faint, distant object slowly shifting position among the stars. This object was named Pluto and was celebrated as the long-lost Planet X that scientists had hoped to find. However, the excitement didn't last long. Pluto turned out to be much smaller than expected, far too small to account for the unusual gravitational effects observed in the orbits of Uranus and Neptune. Those strange orbital wobbles remained unexplained, suggesting that something else, perhaps even larger, was still out there, hidden beyond Neptune. In 1951, Dutch-American astronomer Gerard Kuiper suggested that Pluto might not be a lone object at all. Instead, he believed it was just one of many icy bodies forming a belt beyond Neptune's orbit, a region that would later be named the Kuiper Belt in his honor. This idea remained unproven until 1992, when astronomers David Jewett and Jane Liu discovered a small icy object beyond Neptune known as 1992 QB1. This was the first confirmed observation of a Kuiper Belt object, or KBO, providing real evidence that the outer solar system was filled with many such icy bodies. Over the next decade, hundreds more were found, transforming our understanding of the solar system and firmly establishing the Kuiper Belt as a major region of celestial activity. As astronomers continued to uncover these distant objects, they introduced a broader term, trans-Neptunian objects, or TNOs, a name even to anything that orbits the Sun from a distance greater than Neptune, which lies about 30 astronomical units, or AUs, away. For reference, 1 AU is the average distance from Earth to the Sun, about 93 million miles or 150 million kilometers. As the catalog of KBOs and TNOs grew, the idea of a single massive planet X causing the orbital anomalies started to lose support. Many scientists began to think that the combined gravitational pull of all these smaller icy objects could be responsible for the strange movements in Neptune's orbit. But that theory was challenged in 2003 when a new and puzzling object, Sedna, was discovered. Sedna is a TNO with one of the most elongated orbits in the entire solar system. At its closest, it comes within 76 AU of the Sun, but at its farthest, it drifts out to an astonishing 937 AU. That's 19 times farther than Neptune ever gets, and 31 times the maximum distance of Pluto. Sedna's orbit also raised serious questions. First, if it formed where it is today, that would mean the Sun's protoplanetary disk, the swirling cloud of gas and dust that formed the planets, must have stretched much farther than scientists thought, possibly out beyond 75 AU. Second, for a large object like Sedna to form naturally, its original orbit would have needed to be more circular. Highly stretched elliptical orbits, like Sedna's current path, make the smooth accumulation of material almost impossible due to violent collisions. This strongly suggests that Sedna was pulled into its current orbit by the gravitational influence of something big, possibly another large hidden planet.
Then came another twist in 2005 with the discovery of Eris, another massive TNO with an extreme orbit. Eris travels between about 38 AU and 97 AU from the Sun, further fueling suspicions that something much larger was shaping the behavior of these distant objects. The real turning point came when astronomers began to find a group of even more unusual TNOs, now known as extreme trans-Neptunian objects, ETNOs. These objects, including Sedna and others, share several strange orbital traits. They tend to cluster together in space and follow similar paths, which is highly unlikely to happen by chance. The best explanation? Something massive, perhaps 5 to 10 times the size of Earth, is pulling the strings from far beyond Neptune. Let's imagine a simple scene to explain a complex idea. Picture laying dozens of marbles on a flat table. Normally, you'd expect them to spread out randomly, scattered in all directions. But what if you noticed a bunch of them clumped together in one spot? That would immediately raise a question. What's causing them to gather like that? This is exactly the kind of puzzle astronomers are facing when they look at the orbits of extreme trans-Neptunian objects, ETNOs. These icy bodies, which orbit far beyond Neptune, aren't randomly scattered like they should be. Instead, their orbits seem to be clustered or grouped together in space. Specifically, their perihelions, the points where they come closest to the Sun, aren't spread out in different directions. Instead, they appear to point toward the same region of the sky. This kind of clustering is incredibly rare if it's just random. It suggests something is influencing their orbits, something powerful and unseen. Even more intriguing, the long axes of their elliptical orbits, lines that stretch from the closest point to the farthest point from the Sun, also tend to line up. Statistically, this kind of alignment is extremely unlikely to happen by chance. So what could be causing it? Many astronomers believe this pattern is strong evidence for a massive, hidden planet far beyond Neptune. The consistent direction and shape of these orbits point to a gravitational force acting on them from afar. This idea gained momentum with the discovery of distant objects like Sedna, Eris, and 2012 VP113, which all shared similar orbital traits. Their presence supported the theory that something bigger might be shaping the structure of the outer solar system.
In January 2016, astronomers Mike Brown and Konstantin Batygin published a groundbreaking paper that added serious weight to this theory. After studying the orbits of 6 remote TNOs, they concluded that the only logical explanation was the gravitational pull of an undiscovered planet, what we now call Planet 9. According to their models, Planet 9 would be about 10 times the mass of Earth and follow a stretched-out oval-shaped orbit that takes it anywhere from 400 to 800 astronomical units, or AU, from the Sun. That's hundreds of times farther than Earth's distance from the Sun. When Neptune was discovered in the 1800s, it was found surprisingly quickly. Astronomers used math to predict its location, and they spotted it on the first night of observation. But Planet 9 has proven to be far more elusive, and there are 4 main reasons for this.
First, there's the enormous distance. Planet 9 is believed to be 10 to 20 times farther from us than Pluto. At such distances, it would reflect barely any sunlight, making it incredibly faint and hard to detect, even with our most powerful telescopes. Second, its orbit is likely very elongated, meaning it might spend most of its time in the outermost, darkest part of its journey around the Sun, where it's nearly invisible and out of reach for observation. Third, astronomers are dealing with a huge area of the sky where Planet 9 could be hiding. Instead of having a precise location to check, they must carefully scan vast stretches of space, double-checking every tiny signal to ensure they don't miss it. Lastly, the movement of Planet 9 across the sky is extremely slow. Because it's so far away, it appears to barely shift position, making it even more difficult to spot among countless stars. All of these challenges make Planet 9 a particularly tricky target. But the unusual behavior of ETNOs keeps pointing to its existence, and the search continues, slowly uncovering more clues about the dark, distant outskirts of our solar system. Because Planet 9 is so far from the Sun, it moves incredibly slowly across the sky compared to the background stars. This slow motion makes it very difficult to detect. It doesn't stand out right away, so astronomers must track potential candidates over time to be sure they're looking at a moving object and not just a fixed star in the distance. Due to these challenges, scientists rely heavily on computer simulations to help in the search. These virtual models allow researchers to explore complex behaviors that would be impossible to observe directly. Through simulations, astronomers can test different scenarios and see how objects in the outer solar system might move under the influence of Planet 9. One of the key areas scientists look at is the orbits of trans-Neptunian objects, or TNOs. These orbits are unstable over very long periods, millions of years, because Neptune's gravity can disturb them. In many cases, this gravitational tug might cause them to crash into Neptune, be thrown into the far reaches of the solar system, or be ejected entirely. To better understand this, scientists ran a series of simulations using objects from the inner Oort cloud, a distant shell of icy bodies surrounding the solar system, ranging from 2,000 to as far as 100,000 astronomical units, or AU, from the Sun. They selected 2,000 virtual TNOs with semi-major axes, or average orbital distances, between 100 and 5,000 AU, and perihelia, or closest approach to the Sun, greater than 30 AU. Then they ran 2 separate simulations, one that included Planet 9 in its predicted orbit, and another without it. The results were eye-opening. With Planet 9 included, the simulation showed that it significantly affects the orbits of some TNOs. It changes the shape and tilt of their orbits, something measured using a mathematical tool called the Runge lens vector, which helps describe the direction and eccentricity, or stretch, of an orbit. A perfectly circular orbit would have a Runge lens value of 0, while stretched elliptical orbits have higher values. Planet 9's gravity appears to make these orbits more stretched and tilted. Interestingly, without Planet 9 in the simulation, fewer TNOs ended up getting close to Neptune. In fact, without the planet, objects only came near Neptune up to a distance of about 30 AU.
But with Planet 9 included, the range of TNOs having close encounters extended much farther inward, starting from as close as 16 AU. To verify if their models matched real-world conditions, scientists compared their simulations with actual space data. They used data from 17 known TNOs with semi-major axes over 100 AU and perihelia under 30 AU, while accounting for how telescopes might miss or misreport certain observations. The simulation that included Planet 9 had a much higher chance, about 41%, of producing the patterns seen in real data. By comparison, the version without Planet 9 scored far lower. This big difference in probability strongly supports the idea that a massive hidden planet is influencing the orbits of distant objects. The version with Planet 9 lined up much more closely with what astronomers are actually observing in the outer solar system. Looking ahead, scientists are excited about what the Vera C. Rubin Observatory in Chile will uncover. Equipped with an advanced 8.4-meter telescope, this observatory will scan the entire night sky regularly, keeping track of distant objects like TNOs with unmatched precision. These detailed sky surveys will help confirm whether certain TNOs consistently show the same orbital patterns predicted by the Planet 9 theory, especially those that seem to approach the Sun from distances greater than 16 AU. This mix of cutting-edge technology and advanced simulation could bring us closer than ever to confirming the existence of Planet 9. It may also transform what we know about the farthest reaches of our solar system. In other cosmic news, the James Webb Space Telescope has recently helped scientists refine their measurements of how fast the universe is expanding. Surprisingly, the results have deepened what experts are calling the biggest mystery in modern cosmology, a growing mismatch in our understanding of the universe's basic structure. If you haven't caught up with that discovery yet, be sure to check it out. And if you learned something new from this, don't forget to like the video and subscribe to the channel for more fascinating space updates. Thanks for watching, and we'll see you in the next one.